In section 7.4, we're going to extend what we talked about in section 7.3 with our altitudes and our perpendicular bisectors and our medians, and start to talk about some special points that can be formed with these different segments. So what we're going to look for today is what are called points of concurrency or concurrent points. Now, in generally, a point of concurrency is just going to be a point where two or more lines intersect. And it doesn't have to be an actual line. It could be a line segment. It could be an array, whatever you want. But it's a point where two or more lines intersect. So we're going to look at three special points of concurrence today. We're going to look at the orthocenter, the centroid, and the circumcenter. Now, the orthocenter is a special point, and it is going to be the point of concurrency for all three altitudes. Now, if you remember, an altitude is a segment that is perpendicular to a side that goes to the other vertex. So in the example here, we have this vertex and it is perpendicular to the other side at a 90-degree angle. And the interesting thing about it is if you do all three altitudes in a triangle, they are always concurrent, and they are concurrent at a point called the orthocenter. Now, when we actually do constructions and do this a little more formally, you'll be able to see this well, but we can kind of estimate where these things are. So the orthocenter, what we're going to do is we're going to find all the altitudes first, and then we'll kind of make sure that they are at a point of concurrency. So let's look at this first one first. So triangle XYZ. So I'm going to start with side X or YZ. So we did this one together. So if I see YZ here, then if I go to its opposite thing, X, this is its altitude. So this is the altitude for YZ. So that's one of my altitudes. Now, if I look at another side, let's say I look at this one. Let's say I look at these points, right? So this one, if I look at XZ, then the point across from it is Y. So up here, and if I go straight down to the other side, then this is my second altitude, this second purple segment. So this one's kind of odd because the altitudes are actually sides of the triangles, but the third one will not be. If I rotate to this side, YX, if I take this side and I go to the opposite vertex and go straight down, here is the third altitude. So these three purple lines have to have a point in common, and in this case, the point in common is actually point Z. So in this case, my orthocenter is just point Z. So if I wanted the coordinates of point Z, it would actually just be 0, 0 in this case, because two of my altitudes are just sides of the triangles, and then the other one obviously is going to intersect that third vertex. So I think the next one will be a little more interesting, I don't think, because the orthocenter does not have to be on the triangle. A lot of times it's in the middle. It can actually be on the outside of the triangle. So let's look at triangle DEF. So if I start with E and go perpendicular to this one, this is one altitude, okay? So if I rotate this and do D to EF, so I'm going to start with D and go straight down perpendicular to EF. These are perpendicular, hopefully. And then I'm going to rotate again, and I'm going to go from F, and I'm going to go perpendicular to the other side. Okay? So those are my three altitudes for each side going from the opposite vertex to the side perpendicular. So you can see these intersect at a point, and this point is what we call the orthocenter. It is the intersection of the altitudes. Now the orthocenter in this case appears to be 0, 2, since this is kind of on a coordinate plane, but a lot of times it'll just kind of be in free space. All right, the second point of concurrency we're going to talk about is the centroid. Now the centroid is going to be the point of concurrency. For the median. So if I look at all the medians, they will intersect at a point called the centroid. Now remember, a median is going to go from the middle of a side, so the midpoint of a side, to the opposite vertex. So this is the middle to the opposite vertex, the middle, opposite vertex, middle, opposite vertex. And that is our centroid here in the middle. So if we're finding the centroid, we just find the three medians, and they should, in theory, intersect at a certain point. So here we have RPQ. So I'll start with the RP side. I believe this looks like the middle. So I'll go straight down. It does not have to be perpendicular, although this one appears to be so. So for P, I'm kind of looking for the middle. I'm going to say the middle is somewhere like here, not precisely. And I'm going to go over to R, so there is that median. Kind of the same thing for RQ. The middle, I'm going to say, is somewhere right here. We'll be able to do that more precisely later. So those are my three medians, and you can certainly see that this does have a point of concurrency right there in the middle. So that is called my centroid. And my centroid in this problem is going to be, looks like negative 3, 4. So this is kind of on a coordinate plane, something like that. Let's look at one more. Let's look at this guy. Let's look at LKM. So LKM, we have, well, I think LK is a pretty easy one to do. It looks like the middle looks to be about there. The opposite vertex is here, so there is my first median. If I look at the next one, looks like the middle, I don't know, somewhere around there. And there's L. So there would be my median there. And then the middle, somewhere around here, again, I'm approximating something like this, right? So there is my centroid. That appears to be at 1, negative 2. But there is my centroid point right there. All right, the last one we're going to look at is what is called the circumcenter. Now, the circumcenter is going to be the point of concurrency for the perpendicular bisectors, kind of obviously because that's the last one we haven't done. Point of concurrency for the perpendicular bisectors. Now, so we'll look at our perpendicular bisectors. Now, this is a weird one. It also, the circumcenter is also the center of a circle that could inscribe your triangle. We won't use that information too much, but that is a true statement. So we're going to try to find the point of concurrency of the perpendicular bisectors, which basically cut a side in half and is perpendicular to that side. Now, this is one that could certainly be outside the triangle depending on what you have. So if I look at the middle of these, so RT, the middle is here. So if I go perpendicular, I just like to extend these because sometimes these go kind of some weird places. So that is a perpendicular bisector there. The middle of SR appears to be something like here. And I'm going to go perpendicular to that, which would look something like that. Now, ST is a little tricky. The middle of ST, let's say the middle of ST looks something like that. So if I go perpendicular to ST, I get something that looks like this. So my circumcenter is actually outside of the triangle. This is my circumcenter. Looks to be like, I don't know, 3, 3 maybe. So if I take a circle with that center, it is the smallest circle that would encompass this triangle. Well, it has to have all the vertices in there, so it's kind of hard to see. Let's see if we do it this way. Something like that, right? Where all the vertices are on that circle. Now, again, we don't really use the fact that it is the center of a circle that inscribes the triangle as much as we just use it as one of these points, because we're eventually going to try to figure out which of these points is optimal for our project. So if I look at this last one, we want to find the perpendicular bisector's intersection to find the circumcenter. So the middle here appears to be right here. That's the middle of UV. So I'm going to make a perpendicular line that kind of goes through there. If I look at UV, I'm going to say the middle is here. So perpendicular will look something like this. And then finally, if I look at UW, somewhere like here being the center, perpendicular is going to take me like this. So in this case, the circumcenter is a nice point right in the middle. So if I take a circle that has all three of those vertices in it, that purple point of the circumcenter should be the center. So just a quick way to kind of estimate where these points are. We're using some construction methods and some technology. We can certainly find these very accurately and draw them really, really well.